I can see it.
All right, awesome. Thank you, Avi. I am right now trying to find my chat window. I will go ahead and have that open. I do welcome, as Avi said, interaction at any point. I do like things as interactive as possible. I'm excited to get back in person. I can't wait to be back in person for as much as I can so that I'm able to interact and see people, meet people. But go ahead, please jump in anytime. I do appreciate everyone who's joined in. I'm also going to put up the participants so I can see if anybody raises a hand or anything. So all of those methods for interacting, I'll even ask questions and people just jump in with ideas and thoughts. I want it to be interactive. Let's go ahead and talk about Monte Carlo simulation Bootstrap. Now, we could have just called this uncertainty quantification and probably done a better job of a title, but we're being kind of focused on the tools by using the terms Monte Carlo simulation and Bootstrap. All right, so Avi, you've already introduced all of us, introduced what we're doing here. I appreciate that. What I'm going to do today is I will go through an introduction of myself, just a couple slides about who I am. I will talk about the goals of what we'll do in the next hour. We'll cover the basics. Now, I've actually been part of a full Monte Carlo simulation course once, and it was a full short course. We could teach it all semester, in fact. There was so much to learn about Monte Carlo for sure. But we'll cover some of the basics, the basic building blocks, and that will motivate us to say we need distributions of uncertainty to feed in, and that's why we'll go into Bootstrap. And then all the way throughout this, we'll have a bunch of examples for everything we show in Python. Now, Avi mentioned on our learning management system, you can have access to all of these resources to help in your journey to learn about these topics. Okay, I promise, just a couple of slides about myself. I'm looking through the names here, and I recognize some people, but not everybody. So let me go ahead and just mention my last name is pronounced Pyrcz. At least that's the way we pronounce it based on our 100 years in Canada. I've been told by Ukrainian folks that we don't actually pronounce it correctly, but we do our best. I'm from industry. I did spend many years in industry working on everything I talk about. I did in practice. And I like that. When I teach, I can teach from experience. And I've worked in data analytics before we were calling it data analytics and machine learning. It was more around statistics, statistical modeling, statistical learning, uncertainty characterization, and so forth. And we know that. And I'll say this and I'll say it again. We in subsurface have been doing a lot of this for a long time. We have great expertise and experience. I'm flexible. If you if you jump in here and you're like, I would like to see a different topic, Avi and I would entertain that. Let us know. We'd love to put together another webinar, right, Avi? We're looking at new webinar topics to share. So we take recommendations. Actually, what's funny is we put together like some new content just recently on game theory and such because of suggestions. I'm available. I have an open door policy. People drop me a line. I love it. I love to hear about what people are doing. It's wonderful. I love the feedback. I'm an engineer and geoscientist. If during this discussion, you need me to come at it from the geoscience angle, I can switch. I'm bilingual. I can communicate it in a geoscience perspective or engineering perspective. Okay. If anybody's interested, I do have a lot of content I share on social media. I am on Twitter. I share a lot of positivity and scientific resources to assist people. I'm committed to supporting the community, my students, and working professionals to face the digital revolution. Okay, let's talk about what's the motivation. What's the goal here? Uncertainty is ubiquitous. I like that statement. We just realized that uncertainty is everywhere. In fact, I like to ask my students, is there a single source of information for the subsurface with complete certainty? Anybody by chat window? Do we have any type of data for which we can claim certainty? No uncertainty. Anyone? I'm curious. When I ask these questions, people always wonder how long I'm going to wait. All right, If anybody has any thoughts about what type of data might be perfectly certain, or you can just make the comment that you don't think any of the data we have is perfectly certain, lacking in uncertainty. From my perspective, I would say that everything we deal with has a degree of uncertainty. Core data, you might say, well, that's the reservoir rock. But then we'll recognize anyone who deals with core knows there's all kinds of issues around extraction of core, damage to core, in situ conditions related to the core, and so forth that might disrupt. Even the measurements we make on core have uncertainties and precision issues, of course. And people will say, well, maybe production data might be considered to be precise information, but then where did the production come from? We often have those issues. So I hope I've convinced you that everything we deal with is uncertain. Now, I want to request here, somebody listening, please send a chat, anything, test or anything. I want to make sure we're not facing an issue where people don't have access to chat and are unable to send. Test, thank you. Hey, awesome, I do appreciate, and on the question and answer window. And Rodrigo, howdy back to you. Thank you very much. I do appreciate it. All right, jump in anytime, you all. I want to make sure we didn't have a technical issue. Let's talk about Monte Carlo simulation. If I was to ask you on a test, what is Monte Carlo simulation, and you describe this following workflow, you would get 100% for that. The procedure is this. Model the distribution. Now, that is loaded. We could talk about sampling, representativity, declustering, debiasing. We could talk about scenarios for distributions. There's a lot we could talk about there. Let's say we have the distribution. That's another time. Draw a random value from a uniform 0-1 distribution. We call this a p-value, a cumulative probability value, a percentile value. You get 100% for any one of those. In other words, you're drawing from a uniform distribution on this axis, and then we're going to apply the inverse of the cumulative distribution function to calculate the associated realization. Very simple. You drew a random value of about, what is that? About 0.67. Then you took the 67th percentile by getting the inverse of the PDF. The associated value is going to be 25.9% porosity units. Okay, so very straightforward. You'd be surprised how many of my students fail the following question. What is the distribution of the p-values we use to draw from the model distribution for Monte Carlo simulation? And it's surprising how many students say Gaussian distributed. Do you see that? I'm tracing a Gaussian distribution right there. Can we all acknowledge that would be wrong? The way to think about this logically is that on this axis, it must be uniform, the random values, because the probability would be between the 20th percentile and the 0th percentile, the minimum value, and the 40th percentile and the 60th percentile, or the 80th percentile, the maximum value, 100th percentile. Those should all be equal. And if you start looking at that and realize that each one of these intervals should be equal probability or equally likely to be drawn, that can only be a uniform distribution. Okay, so this space is uniform. And then by inverting through or taking the inverse of the CDF, we get the appropriate density or likelihood to be within a specific range of the values. Okay, and we're going to repeat to calculate enough realizations for analysis. This might not seem so cool. It might seem very basic. You might be, why did I join today for this webinar if this is what we're talking about? Patience, don't worry, it'll come together. The method is very powerful. You can go back historically, Manhattan Project and other places. These types of methodologies were critical to solving major engineering and science challenges. You can simulate distributions that could not be calculated analytically. What do we mean by that? We can build uncertainty models we could not have built otherwise. Now let's go ahead and walk through a couple of definitions, and then we're going to go ahead and justify my statement that it's powerful and we need it. Okay, let's recall the concept of a random variable. A random variable can be defined as we do not know the value at a location or time. It can take on a range of possible values fully described by a probability density function or a CDF, cumulative distribution function, or a histogram. It doesn't matter. Okay. And so this right here is a random variable. How do I know that? Well, we have a specific property of interest, grain size in millimeters. We have a location vector U alpha. That's indicating a location in space or time. And at that location, we have a distribution, a PDF density model that tells us about what could it be at that location. Now, every time we talk about a random variable, if you look, I'm careful. I'm not being sloppy about the notation. I use a capital X. The capital X indicates that it is a distribution of possible outcomes or data measurements. And if we had a specific measurement or what we call a realization from that distribution, we would use lowercase x. Okay, so big X, the random variable, lowercase would be a specific sample value or a realization. Okay, so that's the concept of a random variable. Now we take the random variable concept and we just show this explicitly. A realization is an outcome from a random variable. Now, if you have a joint set of random variables that have correlation between them, like we do in the subsurface in a model, all the cells in the geocellular model, that would be a random function, and we'll make some comments about that. It's represented as a lowercase x. So I've got the big X is the random variable. I draw a random value between 0 and 1, uniformly distributed. I do the inverse of the CDF. The resulting value is realization number 1, 17.2. Porosity, no, this is millimeters grain size again. Okay. Resulting, so in spatial context, we always use this U. Also temporal, we'll want to give it a location vector. Now, if we go ahead and we do a drawing, a realization, this really is called simulation. And we do that for Monte Carlo simulation, as I just mentioned. We do it for sequential Gaussian simulation. All of these simulation methods are using this idea of a realization drawn from a random variable or random function. For intents purposes, we will suggest that each realization is considered equal probable. If you can have scenarios where you have different distributions and maybe they don't have same probability, then we have to cope with that. But right now, we're just assuming one simple scenario, one distribution. Now, the transfer function is very important. It's a term they use in the subsurface in geostatistics, and it does confuse people because transfer function is used throughout mathematics and science for other concepts, and I've confused people before. The definition in geostatistics is any operation applied to a set of realizations of random variables or random functions to assess the behavior over a spatial or temporal interval of interest. The way I think about it, it's the calculation you do with the realization to get closer to dollars, to get closer to making a decision. That's the transfer function. So let me give you some examples. If you are dealing with contamination in the groundwater, in the subsurface, you might do contaminant concentration using some form of reactive contaminant transport that has bioattenuation and all of that cool stuff going on to figure out what's going on as far as the overall contamination. Now, you might have fed into that model a realization of subsurface, perhaps porosity, permeabilities, and so forth in order to do that. Or dilution, if you're working in mining, you'll be concerned with the specific homogenization, the fraction of ore and waste gained material going into the mine, the mill, and you want to know specifically how that's going to respond and what your recovery going to be on the other side of the mill. Pore volume, you might be using a bunch of other types of properties that derive that. Oil in place, you see these can be very complicated, like flow simulation is a transfer function, but also just oil in place calculation using a simple pore volume times saturation calculation. Those are all transfer functions. Let me draw this out for you. This is what it looks like. The general uncertainty management approach with Monte Carlo simulation for the subsurface goes like this. We're going to get all of the inputs for the transfer function. That transfer function, once again, is going to be a calculation that gets us closer to dollars, gets us closer to value, flow rates, oil in place, mineral grades, and so forth. We're going to go ahead and get those distributions of uncertainty for each of the inputs. If you're a machine learning person, think predictor features. You go ahead and you draw from these distributions, apply them to the transfer function. When I take realization number 1 from this distribution, realization number 2 from X2 distribution, realization number 1 from this distribution, and I put them all together, I get realization of the response feature for the machine learning people, the dependent variable for our statisticians, the output of the transfer function. And if I repeat, I will sample and get the output distribution, which I like to call the decision criteria, because that's something you can send right to your boss. P10, P90, expectation, it could be dollars. In fact, if you can get all the way to dollars, that's even better. Get as close as you can to dollars. Okay, so this is the overall workflow. Now, I promised I was going to justify Monte Carlo simulation, because there are people who are going to be sitting here saying, I don't need to do that. I don't need to use this workflow. What I'll do is I'll just figure it out analytically. I know something about stats. So let me give you 3 problems with increasing difficulty, and let me show you it's very hard to do. Now, not at first, though. Let's do problem number 1. The reservoir volumetric uncertainty is Gaussian distributed, a mean of 100 million cubic meters, and a standard deviation of 15 million cubic meters. Calculate the uncertainty in barrels. Now you see this problem is not a difficult problem. We have the initial distribution, Gaussian distributed. You see the central tendency. You see the dispersion right here in standard deviation. The transfer function in this problem is not that complicated, because we have a conversion to barrels from meters cubed, and we have a recovery factor that's constant. Now all we have to do is we need to calculate the distribution for our random variable x, given a constant being applied to it, 0.3 recovery factor times 6.29 barrels per meters cubed. If we go ahead and do that, it's pretty simple. In fact, if you know a little bit about statistical expectation, you can prove to yourself that the expected value of constant times random variable x is equal to the constant value times the expected value. In other words, this central tendency, the expectation, only is you just apply the constant value to shift it. And you would also recognize that the standard deviation of a constant times this random variable x is simply the constant times that standard deviation originally. So in other words, we can figure out the new standard deviation. We can also show that the distribution shape doesn't change. In fact, you can look at the fundamental affine transformation, and it will show you that it's just a stretching or squeezing if you apply a constant to a Gaussian, to any distribution. So it doesn't change the shape. So we know the output from the transfer function without any Monte Carlo simulation for problem 1. So far I've disproved myself. Let's take problem number 2. The reservoir is comprised of 2 units with thickness distribution represented as, you have unit 1. Now, I apologize. I didn't recognize this. This should be Gaussian. This looks like a normal. Oh, sorry about that. It is a normal Gaussian distribution. I could have shown a G or an N. And so it's Gaussian with a mean of 10 meters, standard deviation of 2 meters. This one has a distribution of 13 and 1. And so the problem is this. You have the 2 distributions of thickness, and now you need to figure out what is the total thickness of the reservoir, its entire uncertainty distribution. Okay, so you got uncertainty distribution for unit 1, unit 2. Now figure this out right here. Now, once again, this is not so hard, because the transfer function is literally the addition of these 2 distributions, these 2 random variables. And we're going to assume no correlation. We'll make it very simple. The expectation of the sum of two random variables is just equal to the expectation of the first random variable plus the expectation of the second. And the variances are additive, and the covariance term disappears if there is no correlation between the two. So we can see once again that we can calculate the resulting Gaussian distribution through a simple additivity of the expectations, the central tendency, and an additivity of the variances. Take the square root of that, you've got the standard deviation. Very straightforward. Okay, so I proved myself wrong again. Let's give ourselves one more problem. This problem right here. Calculate the oil in place given the average porosity has an uncertainty distribution that's uniformly distributed between 8 and 15%. Has anybody here ever used the uniform distribution in an uncertainty model at work? Anyone ever done that? I saw a raised hand. Thank you very much. I appreciate that. What would you say about that distribution? What does it mean if you use uniform as far as the uncertainty? The uniform distribution is really a maximum uncertainty distribution. Not good. I love it. Thank you very much. Each value has equal probability of occurring. Not good. I agree. You're basically walking into your boss's office and saying that it's between here and here, and I have no idea what's going on. So we did that. We picked uniform distribution, 8 to 15% thickness, log normal. That happens. We do often see positively skewed, almost log normal distributions for sure. We've got the mu and sigma parameters there. And then we have a couple of constant terms. Now watch what I do here. It gets worse. Correlation. Average porosity and thickness are correlated with a correlation coefficient of 0.82. That can happen. Thicker units where you have higher energy, better porosity. That can definitely happen in a unit. There's a threshold. Now we can argue about use of thresholding, but we're going to say average porosity less than 9%. It's not going to contribute to flow. That's an engineering geoscience choice. Now we're going to take all of that information and calculate the oil in place. Okay, so we got that uniform porosity distribution with threshold applied. We got the log normal distribution for thickness. We got a correlation coefficient between two. We got two constants. Can anybody do this using analytical methods? Would anybody here be able to actually figure out what that distribution should look like? As soon as you start to do things like thresholds, as soon as you start to combine a bunch of different types of distributions, I got to tell you, the wheels fall off the wagon very quickly. There is no analytical expression to figure this out, but we can use Monte Carlo sampling to sample realizations to figure out this difficult problem. We can't do this analytically. Now let's go ahead and take it one more step. Monte Carlo. Does anybody know why we call it Monte Carlo simulation? Where did that come from historically? What is Monte Carlo? Casino, nailed it. Maxim, thank you so much. I appreciate that. Gambling, exactly. The whole idea was, you can imagine statisticians sitting around as they ought to, to do, sitting around wondering about how would you figure out games of chance, solitaire, any of the games, blackjack, whatever it is, roulette, trying to figure out what's the probability of different things happening. The idea of Monte Carlo goes like this. We get the computer to play the game. We see the outcome. Get the computer to play the game. See the outcome. You see what's happening here? Each one of those is a realization of the game. Then what you do is you do statistics on that. You look at the distribution of that. You can actually start to see distributions of uncertainty. You can start to see, maybe you can back out a strategy that works better. You can see the probability of winning and so forth. That is the idea of Monte Carlo simulation. You get the computer to play the game. Now, I keep that in my head. When I think about Monte Carlo simulation, I think about the computer realizing a subsurface possible outcome. It's like it's playing the actual exploitation of the subsurface game. I think it's really cool. Okay, so solitaire. Have you ever heard that when you play solitaire, you are probably creating a unique instance of the game. Have you ever heard that? Its solution space is so big that there's a good chance if you play Solitaire, your game has never been played before, which I just think is fascinating. That's a cool thing. It's a large combinatorial space with many, many possible outcomes. Card ordering matters. Then you have correlations and constraints because of what cards happen to be in piles, what cards were already played. Oh my gosh, it gets very confusing. And then you have strategy. People don't just, I'm bad at Solitaire, but I'm sure there's people who really think it through about how to play it best. So what you do, you shuffle the deck, you let the computer play a game of Solitaire. You might encode some of your strategy into it too. And then you run it multiple times and you see the probability of winning. You could change the strategy and so forth. This is not trivial. Many practical problems have large combinatorials. I've been helping out a little bit with some mining, looking at the mine plan. You know, when we talk about well placements, these are large combinatorial spaces. We cannot calculate this analytically. We need a computer to play enough of the games to develop enough synthetic numerical reservoirs or subsurface resources, and then we count the outcomes. We'd be frequentists, or you can be Bayesian about it, use priors and so forth. It's all good. Common steps for Monte Carlo simulation. Let's be very prescriptive now. We specify the model, the equation. That's the transfer function. It's going to take your set of input predictor features. It's going to get your output. You hope it's as close to dollars as possible. We can sometimes do multiple Monte Carlo simulation with multiple steps to get to the dollars. That's fine. Specify the uncertainty distribution for each predictor feature. Perform Monte Carlo simulation from each distribution. You may have to account for correlations. That gets more complicated. You apply the realization set of the predictor features to the transfer function to get a realization of the output. That's what we're saying here. We use the L symbol to say the index of the realization, and you repeat for L equals 1 through big L realizations. What's the answer? How many realizations do you need when you do Monte Carlo simulation? As many, Lori, nailed it. 500. You know, these are all good answers. As much as you wish. The way I like to think about is this. If first of all, often Monte Carlo simulation can be numerically pretty cheap, in which case you just run many. And I like that. 500, 1,000, a big number, right? Even if it's more expensive, think about it like this. Every time you do Monte Carlo simulation, you get one realization. How many realizations or values do you need to be able to see a P10? Do you think you can define a P10 if you only run 10 realizations? What would be the error around that P10? It would be extreme. No, I agree with you. Thank you very much, Joseph. So I would say you need to consider that. Now, in our book, Pyrcz and Deutsch 2014, we actually use that framework to suggest the minimum number of realizations. And you could use a method like that. I tend to just say use many, 500, 1,000, a large enough number, you can refine it. Here's an interesting workflow right here where we're doing a Monte Carlo simulation in which we're able to go ahead and calculate the uncertainty and saturation given the uncertainty in porosity. So we could use the transfer function could be a known analytical solution to relating porosity to saturation. In that case, we're propagating uncertainty in the porosity to uncertainty in the saturation. I like to think about it that way. We're propagating uncertainty through with Monte Carlo simulation. So I want to give you an example right here and just show you a couple of examples. I want to show you that you can do this in Excel. You could do this in Python. If you don't use Python, you don't code, just run it in Excel, try it out, get some experience. I have examples where I do this that I've shared. Your team is about to drill 2 new formations. The distribution thickness for the formations are 10 meters central tendency, mean, 2 meters standard deviation, and the second unit has 24 and 4 for the Gaussian parameters. What is the mean and variance of the total thickness of the reservoir units? So I'm giving you a very simple example, but then I'm asking the question, what is the P10? Now, this is a percentile P10. If you work with ExxonMobil or a variety of other companies, that's P90 for you, the low side. And you could also have the high side, the P10, P9, depending where you work at. So these are really useful. If you want to do it, you can do this calculation very easily. You could do it in Excel. You could do it in, you know, Lori, I do appreciate that idea. Can you use, instead of an analytical distribution function, can you use the actual data? Very good question. In the next section, right away, we're going to talk about Bootstrap, in which case we will use the data to calculate that uncertainty distribution. And then you're right, you could use the Bootstrap realizations as input realizations for your Monte Carlo. You can do that, okay? And I'll show you that. I hope that helps, Lori. Thank you for the question. I do appreciate that. Very awesome. If you want to do it in Excel, I just want to convince you how easy this is. You could use this command right here to get a random value from a Gaussian distribution with a certain mean and standard deviation. You could repeat that for A formation. You could repeat it for B formation. You could do the summation. Each one of those is a realization of the total thickness. And then you can look at the summary statistics of that. If you're working in Python, I have a workflow that I'll show you right away in which we do some of this. It's very easy. A command like this from NumPy random normal will give you a vector of random values from this Gaussian distribution with these parameters of size L, the realizations, big L. This is a vector of realizations of porosity, volume, saturation of oil. You can apply the transfer function. Look at that. The method of broadcast method for working with vectors. It's a row by row multiplication, and you get the resulting vector with realizations of oil in place. Very, very easy to do. Let's go ahead. I want to show you all, because I don't want to spend the whole time talking here. I want to show you guys a very simple code example right here. And I want to prove to you that, and this is something we have available on the learning management system. This is a very simple interactive Monte Carlo simulation program. Now, if you look at this right here, what you'll see is that this is Jupyter Notebook. By show of hands, has anyone worked with Jupyter Notebooks before? All right. Look at all the hands going up. I love it. I love it. Okay, I'm seeing, oh, okay. I think we peaked at about 1/3. Let me just make a comment for those who have not. It's a wonderful place to prototype and to use the world's brilliance and packages. You can go ahead and open up a Jupyter Notebook. And look, if I double click this, this is a markdown cell where I'm able to put my documentation, links, different types of equations. And if I run that, it actually generates a very nice looking document that I can use to document my workflows, my prototypes. I do it all the time. Then we can load up packages. GeostatPy is the package I wrote for spatial data analytics and geostats. We'll use that. We'll use a bunch of other common packages. We're not talking about Python today. We're not getting into details. I just want to try to encourage. Let me show you this interactive display that I built. Can everybody see that? Is that clear for everybody? What I've done here, I think this is really fun. You can pick to add or multiply. You have 3 random variables. You have random variable 1, 2. Thank you, Jack, Newsrat, and everybody for your feedback. I appreciate it. 1, 2, 3. These are the inputs. You see they're Gaussian. Now I could go ahead and change them to uniform, and now it's uniform from 10 to 30. Now we're not worried about the units, what they mean. We're just trying to demonstrate this idea. So this is 50 realizations of the first feature, 50 realizations second, and just to show you, we can of course change the statistics. You see how I'm expanding it. Third feature, and this is the resulting response, 50 realizations. Now, what I want to convince you of, first of all, is you would never do this analytically. If I take 3 uniform distributions, what is the result of the summation of 3 uniform distributions? Well, this is very interesting. The central limit theorem starts to kick in, and they do start to get a little bit of a Gaussian shape. If you do enough of them, enough variables or features, it will start to get Gaussian. How about the multiplication? That's interesting. That actually kicks in another aspect of the central limit theorem. You start to get more log normally distributed. But anyway, let's not go in too much into that. Now let's look at what happens if we have too few realizations. If I have 1 realization from each one of these distributions and I just apply the addition, that's what I get. I can't tell anything. Now, if I go ahead and start sampling 2, 3, 4, we can all see very quickly that as you increase the number of realizations, the distribution will start to become obvious. You'll start to, it looks kind of uniform at first. It's just so few samples. But when I get it up to about 10,000 realizations, you see how fast that ran? What is the shape of this distribution? It's not quite Gaussian yet. I hope you can see it's a little too flat on the top. It doesn't quite have a Gaussian shape to it. Anyway, I don't want to go too far into this, but this is a nice example for you to play with the idea of Monte Carlo simulation, just kind of some nuts and bolts to work with there. All right, let's go ahead and continue. I'm going to show you a very simple Monte Carlo simulation workflow right here, one that's more complete. Here it is right here. Okay, so this is also available on the learning management system. What I've done here is I've done the typical oil in place calculation. Let me go ahead and run code so everything's working. I'm going to load up a data set. I'm going to simply sample. Here's the average porosity distribution of uncertainty, average volume realizations distribution, and the average saturation. See, this is uniformly distributed, log normal, and Gaussian right here. I'm mixing up the distributions. My transfer function right here, very simple to get oil in place in barrels. I have a conversion here. And when I go ahead and run this line of code, I get the resulting output distribution. So go ahead, check that out, just like I showed in the notes, a very simple workflow for Monte Carlo simulation. Now, I have some other additional stuff here where I actually look at the realizations. So right here is, I've run multiple realization sets so you can get a sense of how many realizations do you need before the answer stabilizes. If I do too few realizations, then if I run it over and over again, I'll get different results. So we can look at when things stabilize. Okay, let's go. I think that was pretty useful. Let's talk about Bootstrap now. Let's switch gears. Why do we care about Bootstrap? Well, you remember we had a Monte Carlo simulation workflow where we had all the inputs going in. They were random variables. They were uncertainty distributions. We need a methodology by which we can calculate those uncertainty distributions. We're going to use the Bootstrap. Now, you could use a methodology by which you can just calculate it using expert knowledge. That's fine. I do accept that. You can also use confidence intervals, as Lori suggests. Those are good ways to get at uncertainties in specific parameters of the distribution to work out the uncertain model. That's fine. We're also going to see that when we do Bootstrap, that the results we get back are going to be consistent with the specific confidence interval. If we Bootstrap to get the uncertainty and the mean, the confidence intervals, and that will match our Bootstrap realizations. Okay. I missed a question here, but your data might not represent the full geologic reality, as best wells are often drilled first. Carol nailed it. You get 100% for that. Exactly. Thank you so much. When we do any of these workflows and we put an input distribution in, we're assuming representativity. We're assuming that these distributions are in fact unbiased. And if you have a bias issue, which I suggest for sparsely sampled spatial temporal data is always, you really do need to do something to address bias, at least check for it. And there are good workflows around declustering and so forth. And we do have lectures where we talk about that as part of our feature engineering data preparation steps. We're going to go ahead and Bootstrap is a statistical resampling procedure to calculate uncertainty in a statistic from the sample itself. Did you hear what I said? It sounds circular, doesn't it? We're getting the uncertainty in a statistic from the data used to calculate the statistic. Okay, that's why they call it Bootstrap. It has that feeling of kind of pulling yourself up from your bootstraps, but don't worry, it works. We're going to use repeated n times Monte Carlo simulations from a data set. Now that's interesting. It actually is using Monte Carlo to do Bootstrap, and then we use Bootstrap in our Monte Carlo. Do you see that? It's kind of turducken. There's kind of a layering going on here, right? I hope people appreciate the turducken reference there. Okay, build the entire distribution of uncertainty for any statistic. The answer is you can bootstrap anything. Let me walk you through Bootstrap. You have 10 sample data. Sandra, I've never tried turducken, but I would definitely like to try it at some point. You have 10 sample data. You get the data and you formulate a, Carol, representative CDF. If you've got to fix it, you've got to fix it. Okay, we're going to do that. Let's assume it's happened. We get a representative CDF. You had 10 data. Now you're going to do 10 Monte Carlo simulations from the data. Okay, so imagine that. Boom, we get a random value uniformly distributed between 0 and 1. It's the cumulative probability value. We get the associated value by doing the inverse of the CDF. That's a realization. Put it here. Boom, boom, boom. 10 times we do that. Then we get a brand new, now listen to this. This is important. That's a new realization of your data set. You see that? Why? It turns out that when you do this, you're not going to sample the same values. You will sample the same values more than once, and you will miss some of the values. We are doing random sampling with replacement. The result is we get a different distribution. That's a data set realization. You calculate the statistic of interest, put it here. Okay, that's realization number 1 of the average. Okay, that's a realization of the average. Then you go ahead, you do 10 Monte Carlo simulations. You see we're repeating now. We get a new realization of the data set. You calculate a realization of the statistic of interest, the average. Repeat, repeat, repeat. If you do that L realizations times. So remember this is nested. You've got N Monte Carlo simulations, L times. And every time you got an L, you're going to calculate the statistic, the realization, the statistic, put it in a distribution. That is the uncertainty in the statistic, the average in this case. Okay, questions, comments? Yeah, this is a good, I do appreciate the question about jackknife. Jackknife specifically is a form of model cross-validation. It's a link to the idea of withholding data and estimating at those data locations. Bootstrap is a method to get the uncertainty in a statistic. Now, I got to be careful here. Bootstrap can be used to get uncertainty in the data set. You see how we just got a brand new realization of the data? That concept is used to pass on to the model in machine learning, and they call that approach bagging, tree bagging. You may have heard of that before, and we talk about that in some of our lectures. Okay, so now we have an uncertainty distribution in the average. Now, what's really cool is this method is originally published by Efron, 82. There are variants of it, like Journal had a variant called Spatial Bootstrap, which I do recommend if anyone's interested and works in spatial. If you are concerned, it seems like it doesn't work, prove it to yourself. Prove that it works. Run the Bootstrap to calculate the uncertainty in the average and compare it to the analytical expression. In this case, the standard error. This is the uncertainty in the average represented as the dispersion, the variance of the average, as a function of the sample variance divided by the number of samples. Okay, it works. It'll actually work, and you can do that. There's all kinds of more advanced methodologies for Bootstrap. I have a publication where I do it for unconventionals a couple of years ago. It's the idea of encoding strategy, or using it to try to understand the value of information. Very cool stuff. One of the most powerful statistical methods of the 1900s, for sure. Monte Carlo simulation and Bootstrap. Assumes the set is representative. Carol, thank you very much. You nailed it. Unbiased and covers the full range of values. If you're just missing data, you can't bootstrap your way out of that. You can't. And assumes all samples are independent, no spatial correlation. Journal 1993 has your answer if you want to do that. And I have examples of that. I teach it as part of our LMS. Okay, if you want to do Bootstrap, you can do it very easily in Excel. I even put this on the LMS, where we do multiple realizations. Carol, you asked if we can work with our data. Or was it Carol? Sorry, I forgot who asked that. Somebody asked if we can just work directly with the data. Oh. Yeah. Lori, you asked if we could just work directly with the data. Here we are. I take a data set with values. I go ahead and I just sample from them with replacement. I get multiple data set realizations. I calculate the statistics, the realizations for each statistic. And here are the box and whisker plots for the mean, the min, the P10, the P90. Kind of cool, pretty cool. I did it in Excel, very easy to do. I have an example in Python where I do a very similar thing. I do this for the problem of you have so many balls, red and green, in a hat, and you're going to draw them and calculate the uncertainty and the proportion. So I have an example where I've done that. And also an example, a more complete example of the Bootstrap workflow. Let me go ahead. I'm going to show you that one. This right here is the Bootstrap workflow. I want to show you this. I think this is fun. I really do. I hope you find it fun too. I see a hand up. Does somebody have a question that I haven't answered? Just to make sure it's not an artifact. Okay. Please go ahead and type in your question. Jayesh, if you do have a question, please just go ahead and put it in the chat window, and I'm happy to address it. Let me know if I missed any questions. Please repeat if you don't mind, if I missed anything. Okay, let's go ahead and talk about the Bootstrap. When we produce workflows in Jupyter, we like to put documentation combined. So it's a standalone document that you can use. Jayesh, thank you very much for that. I appreciate it. So, and I talk even about comparisons to standard error right here. I love the Jupyter notebooks. They're really, really fun. Great documentation. Now what we're going to do is I'm going to demonstrate some good Python Bootstrap. This is some really fun stuff. We're going to load up a data set. Once again, Lori, we're going to go ahead and load a specific data set. We're going to subsample it. Why did we subsample it? Because I want the results to be kind of interesting and I want to be able to explore. So let's go ahead and change it to 20% of the data, 58 samples. We'll come back and increase the number to have a little empiricism, experiential learning together. We'll go ahead and look at our data. The data is a bunch of samples, X, Y, facies, porosity, permeability. This is map-based, not a big deal. Facies are sand, shale. It's a very simple, clastic type of reservoir right here. This is what the data table looks like. There's 58 samples. It's truncated. Let's calculate some summary statistics. This is where we start to ask Carol questions about bias, representativity. Do the statistics look pretty good? We're not going to go into that today. There's always problems, but we're not talking about it today. Let's go ahead. We'll set some min maxes, color maps, and so forth. And we'll produce a nice looking little location plot right here. This is our data right here. Did you notice the number of data dropped from the last run? Because we're 58 data, we were 200 data last time I ran it. We're going to do some declustering. Oh, I actually do declustering. This is a 2-for-1 sale today. We're getting Bootstrap and declustering. I'm not going to talk about the details, but the declustering approach is actually giving us a vector of data weights to account for the representativity due to spatial clustering in the sample. So now what we can do is we can do a couple of Bootstrap realizations. So look at this. This is very simple. We'll take this function right here from random choices. We can do sampling with replacement from the data table, and we'll use data weights to account for the bias. If we do that and we run it, this is the original representative declustered distribution. Here's a realization of the data 1, realization number 2. That's n samples from the distribution. We got a brand new realization of the data. That's super cool. Now what we can do is we can start to do some summarization over all of those. Look at that. We now ran, how many did I run? 1,000 realizations. I calculated the average every time. This is the distribution of the average. Now we could go ahead. Did you see how fast that ran? I can run 10,000. That's not so bad. Ooh, look at the distribution. So well behaved. A little central limit theorem is kicked in. We're definitely getting a nice Gaussian distribution of the averages. And here's the uncertainty and the standard deviation. Very, very cool. Now, there's a lot more things you can do with Bootstrap. You can bootstrap anything. You could bootstrap the Dijkstra-Parsons coefficient. You could bootstrap the Lorenz coefficient. You could bootstrap any statistic or measure. I would challenge you to try bootstrapping anything. All right, let's go back. So if you were interested, I welcome you to try out some Bootstrap. You can formulate a data set. You can use one of our example data sets. You can repeat and do 1,000 samples with replacement. You can calculate any statistic, any realization in any statistic, and you can go ahead and summarize and work with that. We welcome you to try that out. I also have, if anybody is interested, and I'm not going to spend the time right now, but I actually do go into standard statistics and confidence intervals. And what's really, really interesting, if you get into confidence intervals and hypothesis testing, is you can solve those methods using Bootstrap. And so what I've done right here, you can check it out on the LMS. I actually have, and I apologize if I'm giving you a headache by going too fast through this. Okay, I'll go ahead and run it all. I forgot to run it. Okay, you can do that. You can select to restart and run the entire worksheet. And if I do that, what I have, let me zoom out a little bit. And I will go ahead and increase the number of realizations. And I'll increase, I have an uncertainty in the proportion where I have a certain number of red balls and green balls. And then what I do is I calculate by Bootstrap the distribution of uncertainty in the proportion of red balls, the distribution of uncertainty in green balls. And then I show the PDFs of red and green balls on top of each other right there. But guess what I also do? And I think this is epic. While I'm bootstrapping, you see this dotted line right here? That is the analytical form of the uncertainty distribution in the proportion. Using the known analytical form, the confidence intervals, I can go ahead and calculate these uncertainty distributions. Then I compare them to the Bootstrap, and guess what? I said Bootstrap works, right? In this case, I hope you can all see that if you use enough Bootstrap realizations, it converges on the analytical expression. This is a case where we know the analytical expression. I don't want to confuse people. There's plenty of cases for Bootstrap where you wouldn't know. You can't you can't do an analytical expression to get uncertainty in the P13 of the kurtosis. No, you can't. There's just some very limited cases for which we can do this, but we show that they match each other. Okay. Hey, Sandra, I do appreciate your support for the Bootstrap. I really do. I think it's a lot of fun, very powerful. Now, what I'm going to do right now is we only have a couple of minutes, and I need to jump off and go meet with a company. You know how professors are. We always got our hat in our hands trying to teach and help and get student funding. Avi, do you have anything you need to say here at the very end?
No, Michael, I'm good. This was great. I like the workflow example as well. So.
And I did just notice my speaker turned off. Avi, I hope I didn't cut you off.
No, you're good, Michael. I appreciate the webinar. No, I like the workflow example as well. So everything looks good.
Awesome. Any questions? Any final questions from people attending? Jack, thank you very much. I do appreciate it. Thank you for attending. Fun to see it. I love seeing people here during the summer. I know a lot of people traveling, a lot of stuff going on, right? Avi, we're seeing, I'm sure a lot of people are busy and all, but we do appreciate you tuning in.
If anybody wants to review this lecture as well, I'll be posting it on YouTube. So if you follow our channel, you'll be able to check out anything that you missed. So.
I should have dressed up. I didn't know it was going to be on YouTube. I'm kidding. All right, well, good. Sarah, thank you very much. Maxim, I do appreciate your feedback and comments. Very nice. And Carol, thank you very much for your questions, comments. Very nice. I hope it was accessible. That's our goal, right? Avi, we want to be accessible. Rodrigo, thank you very much for joining in.
Yeah, if you just search Datum under YouTube, our channel will pop up. So DAYTUM.
And that was a question from Yanni, right? Is it super easy to find, Avi?
Yeah, super easy to
find. Do you want to pop that in the chat window? Do you think that would be helpful?
I can pop the link, and then if anybody wants to subscribe to our channel.
Oh, yeah. You just asked me the question, what book would I recommend for someone starting in geostatistics? I'm going to sound very arrogant, but I do recommend Pyrcz in Deutsch. No, in all seriousness, we wrote it as a very comprehensive treatment. The second edition is much expanded with a lot of, it's made to be very intuitive to folks. All right. Avi, I better go jump into my next meeting. Is that cool?
Good. Sounds good, Michael. Thank you so much.
Everybody stay safe. Thank you. Thanks a lot, Avi.